Okay, let's continue. We're a little late, but better late than never. And this will advance. So down is advance.
Is it working?
Okay, so I want to thank Hanno for joining us as well and coming to talk about hydrothermal. So you're seeing sort of all the variations of pressure synthesis, which is great. It's such a great tool. I don't want to. I'll let Hanno talk.
All right. Well, more than plenty of loud. So thanks for inviting me to give a talk here. And I was told to talk about hydrothermal synthesis. And I was also told not to talk about my own chemistry. So you'll get a little bit of hydrothermal and you get a little bit of my own chemistry since I don't really follow the rules. But the idea is that this is sort of an introduction to hydrothermal synthesis, talking a little bit about why it works, how it works, what you should think about, problems you can encounter, all that sort of good stuff. Okay, since I think JP said he was going to put these or make these available, there are some references you might find interesting. Obviously, you can't copy them down now. So in my group, we do a lot of crystal growth. That's what I focus on, and we use all sorts of techniques, ranging from just aqueous chemistry, all the way, this one here, to hydrothermal, mild at low temperatures, sort of high pressure hydrothermal, flux crystal growth, and all depending on the type of material that we're trying to make. But today the goal is to discuss the hydrothermal method. Okay. The goal of the hydrothermal method is to make crystals. This is why you want to use hydrothermal chemistry. You can also use it for preparative chemistry, but in many cases, you would like to make some crystals. So, and you hope they look as nice as these that one of my students made. So without going into the other methods, I just want to sort of focus a little bit on subcritical hydrothermal and supercritical hydrothermal. And that really has to do with the temperature regime. So subcritical or mild hydrothermal, you can use these power bombs, and I'll show those to you, versus in supercritical hydrothermal, you're going to have a little bit more, a lot more steel involved in the reactions. In both cases, the advantage is you get good mixing of reagents. After all, you're in a liquid. You can get kinetic phases, and it's a single-step reaction. The higher you go in temperature, the more you're going to push towards thermodynamic phases. The downside, it's, you don't have a phase diagram to guide you, so it's difficult to predict what you're going to make. It's very reproducible, but on the predictive end, maybe not as nice as we would like it to be. So at the most basic level, hydrothermal synthesis is using water as a solvent in a sealed container with temperatures exceeding the boiling point of water, which is 100 degrees C. And the reason people have looked into this historically is it mimics nature's. There's a lot of minerals out there in nature, huge quartz crystals that were all grown hydrothermally. Given nature has more time, I mean, they were not grown overnight. In our case, we'd like the reactions to be done in between 1 and 3 days. If you substitute an organic liquid or other solvents, then we call it solvothermal synthesis. And again, you're in a closed container operating above the boiling point of that particular solvent. So here, nonetheless, I thought I'd show a phase diagram. This is for water. And there's solid, liquid, and gas. So typically when we encounter water, it's a liquid. If we keep heating it, at the boiling point, it's going to turn into a gas. But if we increase the pressure on the y-axis, we can keep it to a liquid until we hit this critical point, beyond which you become a fluid, no longer a liquid. And then the chemistry changes a little bit in terms of what we can do. Doing the hydrothermal synthesis, if you're not volume limited, the pressure you generate is autogeneous pressure, that is, it's self-generated. So if you're in a power bomb, you have both liquid and gas, the temperature determines the pressure. So you can look that up, the tables. You want to know exactly what pressure is at 180 degrees, that information is available. If you go to supercritical conditions, typically both the temperature and the fill level of your container impact the pressure. Okay, and that's because, this is sort of shown here, I took this from the internet. So if you take water and heat it, right, you boil it, you get vapor coming out. If you put a lid on it and you hold it in, then because you build up pressure, you retain liquid water and you have a vapor phase above it. And if you keep going, eventually you reach a supercritical regime. Now, if you look at the temperatures and pressures, right, at 100 degrees, you have 1 atmosphere. At 200 degrees, I can barely read these, you have 15 atmospheres, and at 250 you go to 40. And at the critical point, you have 220 atmospheres. So there's a sort of, not quite exponential, but the pressure goes quite a bit up. And the one thing to notice in this drawing is the increase in the volume of the water, right? So this is what you start with, and when it becomes a fluid, the volume increases. And in fact, it increases quite a bit. And let's see. I'm going to get to the impact of volume on pressure in a second. I have a few other points to cover first. So one thing to ask, since we're going to use hydrothermal synthesis, is what happens to water above the boiling point. So one thing is the viscosity decreases. So things move more quickly, and if you go to pretty extreme conditions, so 500 degrees C and 10 atmospheres, your viscosity is 1/10 of that at room temperature. So the fluid changes quite a bit. You have enhanced mobility of ions that can help the reaction chemistry. The dielectric constant changes. So with increasing temperature of water, the dielectric constant decreases. So what's interesting, as I will tell you more as we go on, the reason we use hydrothermal synthesis is we can dissolve things that we can't dissolve in regular water. So something that's insoluble or really poorly soluble, you go to hydrothermal conditions and it will dissolve. But if you go higher in temperature, the dielectric constant of water drops. Keep hitting the wrong button here. And by 300 degrees, you have the dielectric constant of acetone. So that means your solubility is changing. So something that was happily dissociated into ions is going to have a tendency to recombine and form, and reprecipitate, in fact. So that also means that the solubility of some species you have are going to decrease with temperature. So you have an increase in solubility because of temperature, but you have a counterforce, which is the lowering in the dielectric constant, which for ionic species is going to impede the solubility. The volume changes, okay? And the volume changes quite a bit. As you cross the critical point in the sort of like 20 degrees before to right afterwards, it triples in volume. So if you think about your container, if you have your container half full and you go through the critical point, the water now wants to occupy 1.5 times the volume available to it, and it obviously can't do that. Liquids are pretty incompressible, which means it's going to push against the container sides, and your pressure is going to go way up and go off the sort of phase diagram that I showed you before. Which means when you do hydrothermal work, keeping the volume of your liquid in mind is important. If you exceed the volume capacity of your container, your pressure goes way up. So a friend of mine, Joe Colis at Clemson, he does really high temperature hydrothermal. He does this intentionally because he knows the pressure is going to go way up. And he builds his own high pressure vessels, and usually they survive. But if you buy a commercial system, they have a big safety margin, but if you exceed it, typically they have a pressure relief valve except when they don't. I'll show you one that doesn't, which is in my lab. But anyway, so the point is, if you fill your container to 32% at room temperature and you hit the critical point, you're now full. That's okay. If you're more than full, then maybe your pressure vessel is not going to make it. Or you anticipate that and you've planned for it. Corrosion is another problem. So at the low temperatures, you have a Teflon liner. It's pretty inert. That's why we use it. But if you go to higher temperatures, you can't use Teflon. So you have a steel autoclave. And let's say you work under basic conditions, you're going to have a real corrosion issue. So in cases like this, you need to have what they call a floating insert. So this is something that contains your hydrothermal reaction. It doesn't contain the pressure, it just contains your reagents and your liquid. And you have an outer liquid as a counter pressure. So you can use glass and silica, that's quite nice. You can use metal tubing. So in my group, we use a lot of silver tubing. And the nice thing about a silver tube as well as aluminum is you can cold seal them. So you weld one end shut, you fill it with your liquid and your reagents, and you crimp it closed, bend it over, and really crimp it tight, and it makes a really good seal. Now it doesn't have to hold the pressure in because you have liquid on the outside, inside the autoclave that counterbalances it. So it's strictly to contain your reaction and to preserve your autoclave. Because you don't want that to corrode. Many of them can break pretty quickly if you happen to do that. There's an advantage to glass, infused silica. You don't get metal impurities, right? It's nice and clean. If you use a metal tube, there's always a chance that the metal from the tube will end up in your product. Teflon is nice because it really doesn't react. And in fact, if you use it as a floating insert, you can use Teflon up to 300 to 350. So if you buy a power bomb, they say the upper limit is 250. And the reason is that the Teflon softens and won't hold the pressure. But if you just use it to hold your liquid and not the pressure, you can use it for another 100 degrees. And that's nice in terms of just containing things. In terms of the floating tubes that you might want to use, so silver and aluminum, and then in many people, especially at high temperatures and high pressures, use gold or platinum, but that gets pretty pricey. But they use very small containers, and they're still pretty pricey. But they tend to be pretty inert. Okay, the one reason, and probably the biggest reason we use hydrothermal synthesis is that the solubility can change really drastically as you cross the boiling point. And something that's insoluble can redissolve. So if you do reaction at room temperature, you add A and B together and you get an instant precipitate, that's not very conducive to crystal growth. But if you take that above into a hydrothermal regime, they can redissolve and recrystallize, and you can form nice crystals. So the reversibility of this process is important. That doesn't mean everything is going to dissolve, but many things that otherwise don't will. And sometimes you have to go to higher temperatures or pressures to get things to dissolve. But it's a nice approach to do that and to grow crystals of things that either you can't get into solution at all, the reagents that is, or where the products precipitate so quickly that you don't get a crystal out of it. So these are some of the, this is obviously an old slide from 2000 here, but this is your typical PAR mild hydrothermal regime. This is what your reaction is in. There's a lid, Teflon liner, it goes into this thing, there's a little pressure relief. They've gotten a lot more expensive over the years, but they're easy to use, and they're good to about 250 degrees C. You can use high pressure glass tubes. They are sold from Ace Glass and some other glass companies. They're thick-walled. They're good up to about 180. And the reason they're only good to 180 is not that the glass will give, but that the seal here is going to start to leak. So there's an O-ring and there's Teflon, and you can put Teflon tape around it. But once you hit like 200, things start to come out. But below, like up to 180, they're really nice. The other advantage is you can look into them, right? You can take a look and see what's happening. Can't really look inside here. We run these reactions, the mild hydrothermal ones, in ovens. These are convection ovens. They're programmable. They're about 5,000 a piece if you buy one, but they are good to better than 1 degree C uniformly across the inside. So you can put a bunch of reactions side by side. They're all going to come out the same. If you go to the internet and or to different websites, you can buy, fancy systems. They have pressure gauges, they have reliefs, you can add gases, whatever you want. You can get different size power bombs. And if you go to Amazon, you can find these much cheaper, like much cheaper vessels. And we've bought a few. So far, they seem to work fine. They're not maybe as, the steel's not quite as thick as the power bombs, but they work pretty well. And you can get them with these PPL liners. These are this dark stuff. This is propyl, I gotta read it from here. I can't, so I look up here. Propyl acid lactone, sorry. So this one goes to about 280, which is nice if you want to go to higher temperatures, but Teflon will give out. And you have to buy them, but again, both the metal parts and the liners are much cheaper at Amazon. And, that can make things much cheaper. If you're going to go above, 250 or 280, then you're going to go for something like this. Then you need a floating insert, so silver tube, aluminum tube, or a Teflon pouch. Ken Poppelmeier had published some work where they put reactions in Teflon pouches. You make your own. That works pretty well. The other thing you can do is just thick-walled Pyrex tubes. And one of the reasons you might want to think about that is Teflon is really great, right? It's non-stick, doesn't interact. It also doesn't really nucleate well. Glass tubes tend to nucleate better. And so sometimes if you can't get a crystal in a Teflon liner, a glass tube might get you one. Or you try to add some, you scratch the walls of the sides, and you get it in. These are pretty easy to make out of Pyrex. You fill them, this is the liquid, you freeze it, you take a torch, you seal it off while it's frozen, while you evacuate it, you seal it, you're good. They go to about 180. So these were 2 millimeter wall thickness, 5/8 outer diameter. If you go to 200, about 1 in 10 explode. If you go to 210, about 50% explode. And if you go to 220, 90% explode. So Rachel, who's shown here making those tubes, tried that out and sprayed glass all over places. But so 180 is a good temperature for these. Okay. Hydrothermal reactions, you should think of them as somewhat of a heterogeneous reaction environment. Not everything is going to be in the solution all at the same time. You can have something still in the solid phase. There's a kinetic aspect to it. Not everything dissolves equally quickly. Something's going to be in the solution, something's still going to be sitting on the bottom. So things to think about. The original purpose of hydrothermal reactions, and still today, was to grow really pure crystals. And in many cases of a decent size. And by decent size, we're talking something like this. So big crystals. The geologists were really interested in it because it mimics nature. They could grow things that were found in nature. And then AT&T, for the older generation, they know what the AT&T is. For the younger generation, that was your phone company in America, the only one, the one. And their phones used quartz as piezoelectrics, and they got it from Brazil, and there were issues of getting enough. So they decided to grow their own quartz crystals. And Maudis was working at Bell Labs, and actually Joe Coley's postdoc with him. And he was a incredibly good crystal grower and did a lot of hydrothermal work. And I'll show this to you on the next slide. The early use of the mild hydrothermal, so these people were in the supercritical regime. The mild hydrothermal was really made very prominent by Edith Flanagan, who worked at Union Carbide, and they made zeolites, and then Edith Flanagan and her group made aluminum phosphates and germanates, so alpos. And these are all microporous materials that are really great for catalysis. And then in the early 2000s, people used it for organic and inorganic hybrid materials. So you would have something you pour together, they would precipitate, but hydrothermally you could crystallize them. And you can make MOFs this way and other porous materials. So this is an industrial production of quartz. So they are pretty big. They are done in very large hydrothermal reactors. Basically, you have SiO2 on the bottom, you have a temperature gradient, you have a seed crystal. So each one of these started as a seed. Because of the temperature gradient, you have convection. So this dissolves, goes up here, crystallizes out, and over time, this is not overnight, you can grow big crystals. And you can also grow really nice crystals once you polish them as little gemstones. So industrially, hydrothermal chemistry really is used a lot. And this is in a supercritical regime where they do this. So if you're going to do this in your own lab, there are different ways to do it. You can do an isothermal, that is, you take your power bomb, you heat it up, turn off the furnace, take it out. There's no temperature gradient other than maybe doing heating and cooling. But it's good for preparative purposes. So if you want to make a large batch of zeolites, that's great. If you want large crystals, you have to work at it a bit harder. You can put a temperature gradient in, which usually means you do it horizontally in either a metal or a glass vessel, and you have a temperature gradient. You get things going from the high solubility end to the low solubility end. Usually that's downhill in temperature, but it doesn't have to be. And you can grow crystals that way. Or I think the most common is just slow cooling. That is, you take your system up, you let it sit for a while to let things dissolve, and then you cool slowly. So if you can cool at, I don't know, 5 degrees an hour, 10 degrees an hour, depends a bit on the programmer you have on there, you can get some nice crystals. So Rabino, this is his paper in Angewandte, he was one of the sort of pioneers of supercritical hydrothermal work, and it's a good review article. It's in the list in the front, talks about different things to consider. He looked at this as really a sort of chemical transport reaction. And under supercritical conditions, if you have SiO2 in water, you can actually make gaseous species that can transport and redeposit. If you're at lower temperatures, that's not going to be an issue. So on the mild hydrothermal, there are no such gaseous species that we know about floating around. And he was also of the opinion that although you have sub and supercritical reactions, it's sort of a continuum. And the thing to really keep in mind is when we look at a phase diagram of water, right, that's pure water, but what you're going to use is a solution, you know, that may have concentrated salts in it or other reagents. And the critical point may be way different from pure water. So it's not true that the critical point of water doesn't change. Of pure water, that is true, but if you make a solution, it's going to be quite different. And so it can be hundreds of degrees above the critical point. So The thing is not so much to think about the critical point of water. The thing is to think about the temperature, the volume, and the pressure, and to use the appropriate autoclave for the process. The reason things dissolve well under hydrothermal conditions is they form complexes in solution. So it's not necessarily an ion that's out there, but it's a complex. And in many reactions, a mineralizer is added, and a mineralizer is just a complexing agent. So if you think about aqua regia, which can dissolve gold and platinum, there's two components, nitric acid and hydrochloric acid, right? And it's not the pH, it's the nitric acid oxidizes, and the chloride ions complex and bring gold or platinum out into solution. So really, you can think of the HCl as a mineralizer species. And so you might add hydroxides, you could add halides, lots of things that will change the solubility of your reagents under the hydrothermal conditions. There are cases where your solubility is too high. That is, you do hydrothermal reaction, you cool it back down, and everything's in solution, which is not ideal for crystal growth. So there's two things you can do. Number one, you take that solution, you pour it in a test tube, you put it in the back of the hood, and you forget about it for a while and see if something crystallizes. The fastest step is you add a lesser good solvent to it. So if something is really soluble in water, put some ethanol in there, lower polarity, changes the solubility, and things can nicely come out. Robinot thought you needed at least a solubility of 2 to 5%. That's a great statement, but it's really hard to know what your solubility is since you can't look on the inside. In the glass tubes, you can see it, right? If it all goes in, you know it dissolved. The reaction outcome is really sensitive, probably too sensitive to the choice of reagents, whether you a nitrate, an acetate, a hydroxide, or a chloride. You can involve in situ reductions, either accidentally or intentionally. So if you have an acetate, organic groups at higher temperatures act as reducing agents, and if the electrochemical potentials align, the organic species can dissolve your reagent to a lower oxidation state. So vanadium is a great example. It easily reduces from 5 to 4 to 3, and you got to work on it to get it to 2. But this is based on the so-called polyol process. These polyalcohols were used in the late 90s to make nanoparticles. Basically, you put your nickel nitrate in solution, you add this polyol, that was your solvent, you heat it up, you get high enough in temperature, the nickel reduces, and out come nanoparticles. So the same thing can happen in your hydrothermal reaction, and you can make vanadium 3 and 4, and you can look at the colors and you have an idea what you've done, ideally intentionally. So there are certain advantages. You can get elements in difficult to obtain oxidation states. You can easily crystallize low temperature phases. You can get kinetic phases or metastable compounds. So that's all great. There are things you want to adjust and control. Some are under your control, others are not so much. But crystal growth temperature and pressure. So the higher the pressure, the more dense the phase tends to become. We're not talking here about 150 to 160 degrees C, but going 200 to 500 degrees C, you will make less porous, more dense structures. There are chemical parameters. The solvent, if you don't want to use water, polarity, dielectric constant. If you have reducing components in there. In particular, if you have an organic solvent, consider that it will act as a reducing agent at higher temperatures. The reagents you're going to put in, acetate, nitrates, halides, concentrations you use, do you have a concentrated solution? Do you have a dilute solution? Do you add mineralizers? And also pH can have a huge impact on what will dissolve, what will stabilize, and what will form. There's a significant kinetic factor to this. Not everything dissolves at the same rate. That can simply depend on the particle size you throw in to start with, whether it's fine-grained or really tiny particles, or just the species itself. The diffusion rates, if you use seeds, which mostly we don't, but if you do, then the crystallographic orientation matters. The nucleation rate versus crystal growth matters. So if you nucleate many tiny crystals, they will grow and use up what's in solution, and then you have lots of small crystals. But if you nucleate just a few crystals, they can grow bigger. So we always think that you heat up to dissolve, and then you give it a chance to nucleate, and then you cool. The time at which you just hang out and soak really does depend and influence what comes out. You can get intermediate species. Dermot O'Hare in the, I guess, early 90s did in situ synchrotron studies in England on hydrothermal reactions. So they took a power bomb and milled down the side walls to less than 1 millimeter thickness, actually a fraction of a millimeter, convinced his safety people that that was still plenty to hold in the pressure. And they looked what forms. And he found that things actually form very quickly. But in some cases where they ran an experiment for like 2 or 3 days, they'll see a phase form, and then a few hours later it totally goes away, and then something else comes back out. This is difficult to know if you have a steel vessel and you can't look inside. So it does pay sometimes to run the reaction for different lengths of times to see what comes out. And then technical parameters really is equipment. You know, what are you going to buy? How do you heat it? And various design aspects. I will say that we don't do much of that. We go and look on the PAR website and buy from their catalog, and they send it to us. There are some new solvents. People use ionic liquids in hydrothermal reactions. That works up to about 200 degrees C, which is sort of the limit for organics before bad things happen to them. But you can use that to crystallize new materials. I always think of an ionic liquid as sort of a low temperature molten salt, but doing this hydrothermally definitely is a new push these days. And then there are these older solvents, ethanol, ammonia, sulfur dioxide, carbon disulfide. You know, some are pretty nice, some are pretty nasty. People have used them all for different purposes. Personally, I would stay away from this one. I would probably stay away from this one. This one is okay, but not so easy. The other ones are okay. So just the other thing is, if you want to use you know, ammonia, you have to liquefy it or push it in under pressure with in a different system. Okay. You are really in an electrochemical environment. So elements can change oxidation states. I think we saw a nice example of how oxygen pressure can impact this, but the solution properties, you know, have a huge impact on which species are stable. So the Pourbet diagram, and they were originally known as potential pH diagrams, EH pH diagrams, or PE pH diagrams. Generally now we just call them Pourbet diagrams. They were developed for corrosion studies. People wanted to know under, you know, if you have a low pH at a certain temperature, what's going to corrode, what will be stable. So you can see here there's iron metal, iron 2+, iron 3+, under different electrochemical potentials and pHs. And so you're plotting the redox potential versus pH in these systems. It's a plot of possible thermodynamic stable phases. So you have a boundary, and you can have obviously both species present at the same time. But you can read it much like a standard phase diagram, just with different axes. And importantly, just like a regular phase diagram, it tells you nothing about kinetics. Right? It doesn't tell you how long something is going to take place. It just tells you what thermodynamically should be stable. But nonetheless, they are of interest if you're just interested in, at what pH do you have a better shot to get iron 2 plus versus iron 3 plus, and at what temperature. You can look at the lines in the Pourbaix diagram, and I realize this is simplistic, but it's fine. You have vertical lines, and they separate different species, but in the same oxidation state. And you have horizontal and slanted lines, and they separate different oxidation states. So if you cross across a slanted line or horizontal line, you're going to tend to favor the stabilization of a different oxidation state. Now, as always, change in temperature and concentration is going to mess things up. This is at STP. Hydrothermally, you're no longer at STP, nor do you have necessarily those concentrations. So if you look at, skip this and go here. If you look at the diagram here for manganese at 25 and a calculated one at 300, you can see how they shift drastically by not a significant temperature change. And going from 25 to 300, you're doing this at the expense of manganese, right? There's a big range of stability, and now it's pretty much at low pH. So if you want to go to that temperature and you want to have manganese 2, you want to hang out in this pH range. If you want manganese 3, you go to a little bit higher pHs. Again, since these are sort of one standard concentration and pressure, although when you calculate at 300, you're still at standard concentration, but different pressure and temperature. It doesn't take into account the concentration that's not going to be ideal, but you can use them as just a guide for the trend, right? So here at pH 6, this should work. Here at pH 6, that's not going to happen. So it just gives you an idea of where you might want to hang out. Or if you want to start with manganese 2 plus, you can shift it into manganese 3 plus. So this is a little bit now in some of the details. So solvent volumes matter. So you go and buy a 23 mil power bomb. We typically use 1 to 3 milliliters of liquid in them, so not a lot. And in my group, we make a lot of fluorides. And to make fluorides hydrothermally, you use HF. If you haven't used HF, you need to get training. If you had training, you can use HF. It's fine as long as you don't get it onto yourself. But HF is nice to make fluorides because there's a high fluoride concentration. You use 49% HF by volume. And so one thing we looked at is the impact of concentration, keeping the volume of the liquid the same, and the impact of water versus HF. So we, at the same temperature here, we took this reaction and then changed the HF to water ratio 3, 2.5, 0.5, all the way down to here. And these were the products with this little handy dandy color chart that we isolated. So at 3 mils of HF and no water, you make a hexagonal tungsten bronze structure. If you go down in ratio, then you stabilize an oxyfluoride and a pyrochlor and impurities. Impurity means we don't know what it is. Otherwise, we would have told you on the thing. So maybe a new phase. And then at the lower ranges, you get all of the pyrochlor. If you change the concentration, right, you double everything. And also we're switching to rubidium here, but you make very different compositions. So all these things have a subtle and sometimes not so subtle impact on what you're going to form. So in this particular reaction, just with rubidium, nickel, and vanadium, we're trying to make both tungsten bronzes, pyrochlors, And so the red compositions are made at 220, the blue ones at 200, and this is the volume of HF and made up with water to 3.0 mils. So you can see that, not really changing things very much, you can stabilize very different compositions. And it also means if you do a hydrothermal reaction and you get a mixture of two phases, you can probably tweak it to get one or the other and not both, which is quite desirable. I'm not going to say much about crystal quality and defects, but one thing I tell my students is the conditions you need for a good crystal, like for single crystal studies, may not be the same conditions you want to get a phase pure sample. So if you get a phase pure sample for measurements, the crystal quality doesn't have to be perfect, but if you want to do a crystal structure, you need a really nice crystal, but it doesn't have to come from a phase pure sample. So if you have poor crystal quality, you can change the conditions at the expense maybe of being phase pure, but you get better crystals out of it. If you have inclusions, that really sucks, because there's not much you can do. That has to do with what crystallizes first and what crystallizes second. So then you need to play with the concentrations. And so you have a lot of variables that you can play with. So it's a very multidimensional phase space. And it depends on how patient you are and how willing you are to go down different axes on the phase diagram. The crystal growth rate will increase with temperature because your solubility ultimately drops. So if you're too fast and you get dendrimers, then you want to slow things down, or you want to lower the concentration in your system. If you're going to use hydroxides as mineralizers, and you don't want a hydroxide species in your product, like you want just an oxide, then higher temperatures will prevent that. And you have to work through that. So this is an old paper. They looked at tetramethylmonium hydroxide and vanadium oxide in different ratio, well, in one ratio and as a function of pH. And you can see that they were all done at 185 in the same molar ratios, and you can go from, lithium vanadate solid state material to those having the tetramethylammonium ion in them, to hydrated samples. So the pH can really change the outcome of your reaction, both in terms of the product, but also in terms of morphology. And I'll show you the next slide, I think. So propionic acid is actually better for reducing than acetic acid. And in their reactions, they looked into this and they got VO2. But if they used acetic acid and just up the temperature, they could also go to VO2. So sometimes changing, if you want to do reduction, changing the reducing agent, you can stay at lower temperatures. So in this paper, they show you the morphologies of your crystals under different reaction conditions. So sort of, if you don't like the shape of your crystals, work on the conditions and you can get something better out. So in my group, as I said, I'm going to throw a few things in. We were interested in fluorides and oxyfluorides, and also in making reduced vanadates. And these materials were synthesized hydrothermally. And what we found is if we started with an alkaline earth fluoride, or lead fluoride, versus an acetate, here we don't really have a reducing agent. You get vanadium 5. Once you put the acetate in, it's a nice reducing agent. You end up getting vanadium 4 out of it. So just the choice of reagents can impact the reducibility of your system. There are people who would like more oxidizing conditions. So you can add oxidizing species in it if you're careful. So potassium, perruthenate is quite oxidizing, and it can help you maintain oxidation states of certain species or even oxidize them up. Just be aware that things in high oxidation states sometimes get unstable. So in this particular case, they started with the vanadium-4 and ended up with vanadium-5 in water. So it's a matter of the conditions. You know, you can oxidize things up in reactions, but you don't necessarily have to go there. We had one case where my postdoc was working on cesium vanadium oxides, and these were the reactions he used. So this is heated at 5 degrees C per minute, 250, stayed there for 24 hours, cooled at 6 degrees per hour. And he got mostly cesium vanadium oxide, which we did not want, something that's identified, and then a minor in emphasis, cesium-2 V3O8, which is mixed valent and that we really wanted. And I showed you all these different variables. He tried them all. And the result didn't change one bit. So we had a long discussion on this because he got really frustrated. Can't imagine why. And we decided it was a kinetic problem. So the reduction of the vanadium takes a little bit of time. So when you put the vanadium and the cesium in together, then before the vanadium can reduce, the cesium grabs it and makes cesium vanadate, and you're done. So we said, okay, what if we split this into 2 steps? So we did a 2-step reaction. So the first part is identical, except no cesium carbonate, and you run it the same profile I showed you. Then you open it up, you add cesium carbonate, you close it, you run the same profile a second time, and you get 100% yield of cesium-2 V3O8. So if you're trying to do a reduction, sometimes doing this in 2 steps can really work. And I should also point out it was a nice phase pure product that came out. You can pre-reduce your reagents, so you can make a stock solution of vanadium-3, vanadium-4, and start with that. That's another way, but now you've added just another variable to it, which may or may not work as well. But this is just to show you can go from vanadium-5 with organic species to here, but with zinc you can easily get to all the low oxidation states. And this was just another example of that. So my comment on the 2-step reduction reaction is that it's useful for getting reduced cations in solution, in particular where you use an organic species for the reduction. If you end up getting something with a major product with an unreduced metal species, then this becomes very useful. Okay, so thought I would sneak in one more reaction of our own. So my group works a lot with actinides, and Kristen Pace was doing still mild-ish hydrothermal. So this is at 300 degrees C, so that means we can't use a power bomb. So these were done inside silver tubes, and basically you counter-pressurize the silver tube, because it can't hold the pressure. And she made this uranium-5 borate that came out. These are the crystals she got, which are pretty decent in size. And it's a layered structure with the uranium in a pentagonal bipyramid, and the borate groups connecting them, and then in between them the sodium ions go. So this is something you cannot make in a power bomb at 200 or 220, but if you go to 300, you actually enter a regime where not that many people have worked, mostly because, you buy your power bomb, 250 is the limit, everything you do is below 250. People don't want to do supercritical, that I get, but this is sort of intermediate. So this is your power bomb, this is the intermediate regime, this is a pressure relief, which is nice. Then you can put a bunch of tubes in there at the same time. And then this is for high pressure, supercritical reaction, that's a ZurLoye alloy. No pressure relief, you just close it, heat it. We have a bomb room under the roof with sand-filled doors, solid concrete walls, and a blowout panel on the roof. But we haven't needed it yet. So you just need to know what the pressure limits are and the temperature limits and not exceed them, accidentally or intentionally. I'm going to just skip these things. I was going to show you one more. These are neptunium crystals, just because they're really nice. So this is done, I mean, you look at this reaction, it's pretty easy, right? You heat 5 degrees C a minute, soak, cool, out comes the product. Now this was all worked out, not with neptunium, but with other reagents. But you get nice crystals. And the other thing to notice is we're limited to 5 milligrams of neptunium per reaction. So we actually have different Teflon inserts. They're very shallow, so they're mostly solid Teflon. So there's a lower volume that we use. And my student Kristen came back and she said she needed to order 5 more. And I said, why do you need 5 more? You just bought a whole bunch. And she goes, yeah, but we only use them once. So I was like, okay. So good chemistry. I'm going to skip the hydroflux. And I'll end here with time for questions, hopefully.
Okay, questions?
Why, so whenever I'm doing things, I try to avoid introducing water into anything. So like what would you not use hydrothermal to support lysis? What does it seem to incorporate? Because it seems like you get like pretty good sized crystals.
I mean, I don't think there's a class of materials you couldn't use it for. If you're going to make something that's really water sensitive, don't use water, right? Just use an organic solvent. And that's one reason in the list of old solvents, there were some really strange ones in, because that's what people were doing. But you can make sulfides hydrothermally. The key thing is, and it's sort of counterintuitive, right? You make something that's water sensitive in water, then you take it out, and then you have to keep water away from it, because if you don't, it degrades. But you can make sulfide and selenite crystals that way. So that's quite doable. Mercury Candicetus published a paper on using hydroxide melts to make chalcogenides, and you're like, oh, this doesn't make any sense, right? You think, yeah. But it works, right? So if you don't want water as a hydrate in your product, then you just need to go to high enough temperature. The higher you go, the less, you're not going to get hydrates, you're going to make solid state structures.
Thanks for the nice talk. I have 2 questions. One is, how high purity do you use for the water for the synthesis? Can you use just a tap water?
I would say my students, I'd like to think they don't use tap water. I think we have deionized water that comes out of the tap that they use. But it doesn't seem to make much of a difference. I mean, you don't want to use water that's full of ions, that interferes, but so we just use deionized water, but we don't have a, ultra pure water.
The next question is, actually it's my first time to hear the neptunium compound. Then what are the interesting properties of the neptunium fluoride?
So I run a DOE EFRC, Energy Frontier Research Center, and the goal of our center is to make nuclear waste forms. So we make uranium, neptunium, plutonium, and americium compounds, and going forward also technetium, so that you put them in a stable crystalline matrix that you can then, pack up in drums and put those away for, 250,000 years. So that's, but because DOE, we're funded by basic energy sciences, we're not to be practical, so we can't actually make a waste form. We can only study the chemistry that will lead to waste forms. So that allows me to apply all my crystal growth skills to make just neptunium, plutonium compounds. And then we try to measure as many properties as we can. The difficulty is finding someone who's willing to let you put a radioactive material into their instrument. It's really amazing how freaked out people get. It's not like we would spray it in that would be contained. But, so I try to have most instruments of my own, so I can, then it's okay. But yeah, so we've made lots of neptunium and plutonium compounds.
John, do these power bombs or the Amazon bombs, whatever, have a lifetime to them? Or you sort of use them indefinitely? Do you need to keep track of how they've been used?
So in principle, you should keep the insert with the metal container, because they do sort of, as you heat them up, they form themselves to it. But I would say my students don't always do that, so that's not so critical. After some time, the Teflon liners actually pick up part of the reaction. That is, they're somewhat porous, and you can, especially if you work with amines, they will go in and weeks later come back out, and you make a compound that, has a ligand in there you didn't add. So we replace them every so often. We just, but I would say they typically last 1 to 2 years, except if my students do something inadvisable, and then they don't last so long. But the ones from Amazon, we've only had maybe for a few months, so I don't know about longevity, but they are so much cheaper, it doesn't really matter. I mean, it's like 1/10 of the price. So even if they only last half as long. And it's sometimes nice, so students tend to use the same liners for the same reactions. You don't want to switch elements, that can be a problem, but otherwise they're pretty good. So that's one advantage of, let's say, putting your reaction inside a metal tube. That's a clean metal tube on the inside. You're not going to contaminate it with anything else. And the autoclaves themselves, if you use the higher pressure ones, that's all steel, which is not to say part of that can't come in. So which is why you don't want to use a corrosive environment, because you will ultimately then corrode the steel itself. And they do tarnish over time. So if you have an old power bomb, it looks like it has an oxide coating on it, which it does. It doesn't impact their functionality.
Any other questions?
For the glass vials, so some people grow mobs, like in scintillation vials, I've heard, we just cap them and put them in the oven. That seems always kind of dicey to have a leak or even an explosion in the scintillation vial. And then I saw in you had these thick wall ones with that had the threading at the top. Do you know how leak-proof those are, and where do you buy those?
They're from Ace Glass. They are high-pressure vessels. They come in all shapes and sizes. As I said, to 180, they're leak-proof. Beyond that, the Teflon seal, which is just it's threaded in, and we wrap it thickly with Teflon tape so that it's a really tight seal. That's about the upper limit, and it starts to leak. But if you're going to use them like between 140 and 180, they're great. They're not that expensive. You can get them in small sizes, big sizes. And so it's a nice thing if you have a new student to just try these. And their lifetime is limited by how long it takes for someone to drop it.
Alright. Is it Pyrex or quartz?
No, they're Pyrex,
Right.
but they're very thick-walled. So I can send you the web link.
Yes.
So follow up on that, if the amount of credit they can have or the temperature they can go to is determined by how deep the Teflon is, have you considered like instead of using the Teflon software, just sort of, how you do something like you do in flux growths where you just read a neck and then like seal over a neck. So that way you don't have any Teflon issues that can close and you require this?
Oh, sure. I mean, you can put, make a Pyrex ampule, put it inside an autoclave, counter-pressurize with water, you'll be fine. Provided, if you fill it too much, right, and you go supercritical, and then the internal pressure is going to pop this thing apart. So when you do a supercritical reaction and you do put an insert in, you have to really think about the relative fill volumes of the insert and of the autoclave itself. The autoclave has to have a higher fill volume than your tube. If not, the tube won't survive. But yeah, so you can, and whether you use Pyrex or fused silica depends on the temperature. If you're going to go to 600 degrees C, you want to use fused silica. If you're going to go to 350, Pyrex is totally fine.
Okay, any final questions? No, okay, thank you, Hanno. Okay, so we're running a bit late, but we're gonna have a 20-minute break. We'll start at 11:20. And we will hopefully be on time again after Frank's talk for lunch at noon. And yeah, okay. Sure, you want me to? Well, maybe there's this one.